Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. What we have seen in the previous lecture is a series network or a tandem network wherein our quantity of interest, which is basically the number in the system at each node, was the joint distribution of this was given by the product of their marginal distributions, right. So, that is what we have seen. Say for example, we had this kind of network is what we had it in mind, for which it was happening that the joint distribution is given in terms of the marginal distribution. So, it is really a truly product form solution even in any sense that you look at it. Okay. So, this a similar thing is possible, like we could understand that how this is resulting in the analysis is from the knowledge of Burke's theorem, and it is possible, right, that similar kind of analysis can be taken forward to feed forward network, like where also similar things can easily be followed without much difficulty. Okay, that is what we have seen. Now, in this situation we have assumed that all the nodes have infinite capacity, meaning that there is ample space for queuing in front of every node. So, whenever it is passing one node, if it wants to go to the another node, in the destination node there is it can queue if it is not getting the service immediately. So, there is always the ample capacity to hold any number of customers in waiting in any particular node. That is what we have assumed, and that is what we are going to assume later on also. But if it is not the case, right, in reality nothing is infinite, right. It is always the case that there is a finite amount of space only is available between the nodes. So, if that happens, and that is what is called as blocking effect, right. So, we have seen in single queue also like it could be blocking effect, which means that if the capacity limitation is there with respect to nodes, then blocking occurs. Of course, there are a general notion of blocking, but even otherwise also blocking can occur. But for us blocking means that a customer, after having completed the service at say node I, he wants to go to node J, but node J has only a finite capacity, meaning that it can only a finite amount of customers can queue in front of it to get the service, and that limit is reached, which means that capacity is full. So, from this, after service completion, now he cannot move to the destination node immediately. So, such an effect is what is called blocking. In a single queue, right, what we have done is that we have assumed that the customers who are coming when the system is full are last to the system, right. Then we looked at the parameters of that, like what would be the probability of that and how to minimize or how to create capacity in such a way that you want to be connected. So, you want to study all those things, right. But in a network scenario, such a loss in between, right, if it is happening at the arrival point, it is a different matter, like one can treat it as if it is a single queue. But if it happens when starting from one node to the other node, if it has to happen, that may not be a realistic situation. It can happen, it is not that it cannot happen, but then it is not a realistic situation in many situations, right. So, it is not a practical option, you keep only that as one of the as a only option is not practical for networks of queues. So, but then how you will treat that particular scenario, how you will make the system to react to how the system will react to such a scenario depends on what kind of policy that you are going to adapt when blocking happens. Okay. So, this blocking characteristics could be of different types. We are seeing few of them, like for example rejection blocking. Okay. This is basically what we are seeing it in single queue, which is basically once the customer is blocked, he is forced to leave the system, right. And this forced to leave thing can happen only in open networks. Obviously, in closed networks, since no customer can leave or no customer can enter, that will not happen. So, this kind of blocking, if that is the policy, then this is similar to what you are observing in case of single queue. This is called rejection blocking, means you reject when the customer is blocked. The other is transfer blocking. This is what typically normally one assumes. So, the blocked units wait at the current queue after having completed its service. Now, it cannot release the server. Okay, server is also like cannot go to the other customer server because the current customer has not yet left the system, and this current customer who has already completed the service cannot move to the next node because there is a blocking there. So, this is what is called as transfer blocking. So, he will wait with the current server as long as he is able to move to the destination node. So, this is called transfer blocking. And then repetitive service blocking. The blocked job goes to another service at the current node once he is not able to move to the destination node, and this cycle can repeat also if necessary, right. There are even other different policies like how one can do. Okay. So, rejection blocking, transfer blocking, repetitive service blocking is some of the common types that one occur depending upon the scenario, but the analysis of such queuing networks where blocking occurs is much more complex and it may not have the product form solution. Recall, in a series network, what we have done, though the network is in series, the joint probability of number in the node 1, number in node 2, number in node 3 and so on, number in node k is given by the product of the individual distributions, which means that what you can treat particular node in isolation, you analyze it, you get the quantity, then you can get the quantity for the whole network. That was the scenario. That is what the advantage of product form solution. But here like it may not have product form solution, as you would see now with a simple example. Say how things gets complex is just want to highlight. We are not going to go very much in detail, for which we consider a 2 node series queue, but with blocking. Again, in a very simple situation, that a very simple 2 station, in each station there is a single server, but no queue is allowed to form at any of the station. Okay. Arrivals follow a Poisson process with rate lambda. Service times at the 2 stations at the 2 nodes are exponential mu1 and exponential mu2. The blocking policy is transfer blocking, which means the customer will wait with the current node until he can move to the next node. Okay. That is what is the scenario. So, the system in our earlier model, this could be represented as MM11 and the output goes to the next node where dot M11 is what is the scenario there. Okay. So, this is what we have. Now, you see here the possible system states are 0 0, 1 0, 0 1, 1 1, which is much like the normal series queue thing that you can think, and also B1 where these numbers 0 0, 1 0, 0 1, 1 1 represents the number in each of these nodes. For example, 1 1 means one customer in node 1, one customer in node 2. Since it is MM11, there cannot be more than one. So, we have to here. This node B1 describes a situation where a customer is finished service at node 1, but is waiting for the server at node 2 to become free, is what this be. So, you have really now 5 system states, and if P n1 n2 is the steady state probability of the system, then they satisfy a set of equations here, which is one each for each of these states, is what then you can easily understand that from 0 0 it can go out only if there is an arrival. In this case it will move to P 1 0, right. So, it comes here, and from 0 1 with the service completion at node 2 it can come to 0 0 2. So, you can write down this in the usual manner, right. For similarly for 1 0 it can go out of this, right, if there is a service completion, right, then it will move to the node 2, right, and from 1 1 with the service completion at second node it can come to 1 0, or 0 0 with an arrival it can come to 1 0. Similarly, for 0 1 it can come, right, from 1 0 after a service completion, right, it can come to 0 1, or with block 1, right, with mu 2, if the customer in node 2 is released, then from block 1 it will move to 0 1, and from 0 1 either an arrival can happen to make it to P 1 1, or a service completion would make it to this case, right, at mu 2 will bring down to 0 0, right. Similarly, 1 1 and B 1 also you can write. So, this is set of equations. Now, what one can do in principle as usual, now all other probabilities can be expressed in terms of P 0 0, and you can use the normalization condition to determine what is P 0 0, right. But the complex, and then you can obtain the performance measure. So, given now for example, even in this particular case given certain parameter values, I will get a set of equations which you can easily solve to get the quantities, no issue, right. But the complexity is, it is very easy to see from this set of equation itself, like if you start allowing, suppose instead of 1 there are 2 customers here, then one more state will come, right. Like this it will expand, right. But the point here is that if you allow positive but finite queue capacity in front of each node, this will expand but the complexity is that you have to write the balance equation for each possible state. Conceptually it is fine, right, you can write down whether it is even 1 million, you can think that conceptually you can write down, but practically that is not a feasible option, right. Compare this with respect to the non-blocking network that we have considered earlier, series network. In this case, you just have to treat a node in isolation, but here you have to keep it together only. And if the nodes are large and if the capacities are large enough, right, then you can see the imagination that you have to handle the whole thing together, because it may not have product from solution, right. So, for large but finite set, one can still use numerical, but otherwise it is very difficult to analyze such a. That is why we say that this is much more complex, but blocking is relevant, and with blocking effect has to be analyzed. So, one has to handle it at some level, but things are complex, which in our normal scenario, like we would not like to venture into at this point of time, right. If those who are interested can look into that. Of course, there are books on networks with blocking itself because of its relevance. Okay. So, that is one can look into that. Okay. This is about blocking. Now, we will not come back to this blocking aspects later on, but we will be considering much simpler ones. Okay. Now, we generalize. Now, blocking we have stopped, we have series we have done. Now, in the series context itself, we have now given the idea of the effect of blocking in a queuing network, what it can have. Now, we will consider truly a full general open Jackson network, right. So, what is that? So, recall as described earlier, an open Jackson network means this is a network of say k service nodes. Arrivals at node I is according to Poisson process with rate gamma I. Service rate, which is exponential at node I, is mu I, and Ci servers at node I. routing probability is Rij, which is independent of the system state, and Ri0 denoting the probability of exiting the network from node I, and no limit on capacity at any node, which means no blocking. Okay, this is what we have. So, we have a Markovian system here, and the state of the system can be described via the number in the system in equilibrium, because you are looking at in equilibrium. The number in the system in each of these nodes, which we call it as Ni, which is basically number in the node, means in queue and in service at node I in steady state. As usual, what like in a series case, what we want the joint distribution of this, which is what is given by this, the probability of N1 equal to N1, N2 equal to N2, and so on, Nk equal to Nk, which is we denote it by P in the subscript N1, N2, N2, and so on, Nk. Okay. Now, once we have this, we know once we have the joint distribution. Now, suppose if I want the marginal distribution of N1 alone, then I can sum over the remaining indices to get this marginal distribution, and I can obtain. So, any number of joint marginals, anything I can obtain it once I have this full joint distribution. That is what our objective is to see, like in series case. In series case, we saw that this breaks into product of the marginal. So, in a much more open general Jackson network, again we were interested to see how this can be obtained. Okay. Recall in the previous class, like we have in the previous lecture, like we have drawn this to just to depict one typical open Jackson network, where there are k nodes. In each node there are Ci number of servers with the rate mu I, capacity is infinite under each node. This red color arrows depict the arrivals from outside, and this purple color arrows depict the departures from any particular node to outside world, and this green arrows depict the movement or routing of customers from one node to the other according to certain probabilities. That is what we have depicted here. For example, from here either it can go out or it can go to node 2, node 3 and node k possibly, right. There could be a number of nodes in between, doesn't matter. So, this is a typical example that we have depicted. So, just recall, this is what is the much general open Jackson network. Open because there is at least one node in which customers can come in and at least one node in which customer can go out, apart from movements between the nodes, right, which is given by this routing probabilities from each node, right. This is what you keep this in mind. Now, whatever we are going to analyze this particular network is what in this generality, right. Now, suppose this has feedbacks. Now, if you want feed forward network only, then we have to eliminate the feedbacks from here, then you will get the feedback. Feed forward network, it can still be in the open Jackson framework, but without feedbacks. But this is much more general is what then we have it in mind. Okay. Now, for ease of writing down, like the vector n1, n2 up to nk, we denote it by n bar as the sim notation, and in this n bar, if the ith element is 1 plus than this ni, then this is n bar I plus to denote that it is basically in the ith element it is ni plus 1, and similarly n bar I minus mean in the ith element it is ni minus 1, and n bar I plus j minus means in the ith element it is plus 1 and in jth element it is minus 1, right. That is what we could see, and for now, right, we are assuming single server system. For now, we will generalize this to later C server just for understanding, but otherwise things will become a little complex. So, we will assume that there is a single server in each node, though this generality is C servers. We will come back to the C servers in. For now, we will assume that this is a single server at each node. It is what is the scenario that we are assuming. Okay. Now, if that is the case, then the global balance equation can be written down for the state n bar with this condition that each of these ni's are at least 1. So, none of these ni's are going to be 0 in this equation, right. That is what is the general equation, that's what general set of equation that one would have, and this is what it is, right. So, you can easily understand the flow in and flow out, right. Say for example, what is the first term tells, right. The system what was in n bar I minus, remember n bar I minus is that the ith element is 1 less, okay. Ith element is 1 less, and with the gamma I an arrival can happen to make this ith element to n bar. So, that is what will happen. So, this basically this with respect to n bar is we are writing it. The left side is the flow into the state and this is flow out of the state, the right hand side is, okay. So, it was in state n bar I minus, means ith element was 1 less, and with an arrival, external arrival, it can come to n bar. That's, and this I could be anything between, any node between 1 to k. So, this is what is with one arrival, it can come to n bar, arrival at any of these nodes. So, I is equal to 1 to k. Now, similarly here, right. So, it was in n bar I plus j minus. So, what was that? In ith element it was plus 1 and the jth element it was minus 1, and service is completed at ith node with rate mu I, and from there it is going to make a movement from I to j, right, from I to j is what then can happen. So, that the total state now it will become n bar, right. Now, this I and j could be anything except that they are not the same. So, that is what this quantity is, okay. The third one would be it in the ith element there was plus 1, right, plus 1, and a service completion happens, and with probability Ri0 it exit the network, right. So, that is what this term would be, it could happen from any of these nodes. So, this is what is the flow into the state n bar. On the other hand, right, if it is in n bar, but its service is completed, right, but with probability 1 minus Rii, it will be going out of the state n bar, okay. So, with Rii it will remain there, but with 1 minus Ri it will move out of state n bar, and hence you have this expression. And similarly here it was in n bar and any arrival would take this to out of the state n bar. So, this is what is the global balance equation. Now, if this is the same equation will also hold for the case of ni equal to 0. If we set the terms with the negative subscript terms containing negative subscripts and terms containing mu I when corresponding ni is 0 to 0. Okay. If you set those terms to 0, then appropriately it can come, right. In all the terms, now if you just write it down and if you set that such terms equal to 0, that is basically the equations corresponding to the boundary states, right. So, you will get for any 1 zeros, 2 zeros, 3 zeros out of this k number and are all zeros whatever is the case. So, if you get from this one can write down in effect the balance equation for the boundary states. Okay. So, this is a generic one, that is what we will keep that in mind, the generic one we are keeping it in mind. Okay. So, this is what is the global balance equations, right. Now, we need to solve this to get P n bar. Okay. Jackson, so how do we do that is what is this significant and very important work of Jackson. He showed that the solution to the balance equation is in a product form, but here the product form, by that what we mean is basically we are assuming that if P n bar, if it can be written in this form, that some constant times rho 1 to the power n 1, rho 2 to the power n 2 and so on is a product, right, rho k to the power n k, right, or it is some constant times a product of some function of ni's, some function of ni's is what then you could call it in this in general. Okay. So, this definition of product form is less restrictive in the sense that we do not require in this form of definition that the C need not separate into an actual product, right. But if it so happens that is still product, like in a series network case, it did happen that the C itself was separated into product of the individual quantities. So, that was nice, very nice. So, that is what is product form. Some people call that as a product form, but this definition is less restrictive in the sense that C need not factor into products. Okay. So, what he showed is that the solution is in this form is what then he showed. Okay. And he gave the, that is what is, so this we will give the solution, that is this, and then show that it satisfies the balance equation that we have just written down. Okay. And this is also called as Jackson's result or Jackson's theorem for open network. Many people would like to call this as simply as Jackson's theorem for open network, mean that the solution to the joint distribution is what is given by this Jackson's theorem, and that is what we are calling it the solution. Now, to do that, what we have to have is that, so we need to find out this lambda i's. What are they? This is the total average flow into state or node I. Okay. This could be external or this could be internal. Internal means it is coming from some other node. External means it is coming arrivals from outside. That is the reason like we usually call it from external arrivals lambda I, but here we did not call it lambda I, gamma I, because lambda I, we want to call this as the lambda I, that is the only reason. Otherwise, if you call that as lambda I, this you have to call by something else for convenience anyway. Now, how do we get this lambda I? Remember, we are given gamma i's and rij's, right. So, now, if it has to satisfy the flow balance at each node, then we need to have this traffic equations, the flow balance equation, or this is also called as flow balance equation at each node for the network in a way. That is what is called traffic equations, because we want to compute this lambda I, and that is why we are calling it this way traffic equations. So, the traffic equations need to be satisfied. Now, what is this traffic equation? You understand the spirit, it is exactly same as what we have been doing it. So, if I denote lambda I is the total rate of flow into node I, right, which means it is the combined flow of both external and internal arrivals, then lambda I would be gamma I, which is basically the component corresponding to the external arrivals gamma I, plus then it has to come from the internal nodes, right. Now, for the jth node, it arrived at the rate lambda j, and from out of this rate, right, rji is the proportion of arrivals or customers that comes to node I, right. So, this can be j can be from any j, right. So, even from its the same ith node itself, right. So, this is what is the total of the internal flows into node I. This is the flow into node I external. So, this lambda I is equal to this, right. Now, if you write this in matrix vector form, it is basically lambda equal to gamma plus lambda times r, and this r is what is called as routing matrix, which tells you like from where to where the flow will happen. For example, in this particular case, like these entries, right, R1, R12, right, there is no feedback here. So, the self feedback is not there, but otherwise R11, R12, R13, R14, R1k, R10 all put together is what is probability 1, that is what you will have. So, this matrix is between these nodes, between the nodes of the thing is what is given by this routing matrix, right. So, this is the routing matrix is R. When we say routing matrix, it is what is called, this is it gives the probability of moving from one node to the other node at the end of service completion. So, the solution to this equation is given by simply lambda, which is equal to gamma times I minus r, this identity matrix I minus r to the power minus 1 or inverse of I minus r. This inverse exists as long as there is at least one node which for exit and no node is totally observing. So, as long as that is there, so this inverse would exist. So, meaning that this under that condition, this system of equations becomes linearly independent and you can find a solution to this system. So, that is what will give you. Now, once I computed this lambda I, which is the, if I look at here, so I consider all these things together, I compute this, all these arrivals put together, in a way I am computing the rate, right, for each node, here, what is the total rate of flow into state, that is what will lambda I will give you. Now, once I have this lambda I, then rho I can define to be lambda I by mu I, and we know that the network will be at equilibrium if each of these nodes are at equilibrium, which can happen only if rho I less than 1. Then what the solution to that is that the steady state solution to the balance equation as given by Jackson is basically P n bar, which is P n1 comma n2 comma nk, which is equal to this quantity. Now, you can see here, right. So, this is as if it is like this, right, you are seeing it here, right. So, which is a true product of the marginal distribution. So, the C times rho 1 to the power n1 and so on is what we have written, but that C actually factors into the product of 1 minus rho i's, and hence this is actually factors into this. So, which is also similar to what you had seen it in the case of a series network, right. So, this is what is Jackson's solution is, or Jackson's theorem gives you the solution to this open Jackson network as this in case of single server. That is why we are getting, we have taken single server just to take some simpler form of solutions like this to exhibit, so that the balance equation is writing it easy, and then this is also easy to see here. Okay. Now, so what are the implications of this result, right? So, once the traffic equations have been solved and you have obtained lambda i's, right, then this is as if right, you can see that this is exactly P at n1, P at n2 and so on, P at nk is a product of the marginals, is what you are actually seeing it as if it is happening here, right. So, this is what we say is a true product of the marginal distribution. So, because of this one, it is not just the product form the way we defined, but because of the product form of the marginals. In terms of marginals, what this implies is that the individual nodes may be considered in isolation, just like we have did it in the series tandem network case, and hence and then putting together you can get the joint distribution, right. It is a very powerful result in that, because such a complex network you are seeing, but the analysis what ultimately is if the network satisfies these properties, then what you are seeing is that individually I can treat them as if it is a separate entity and then I can put together and do. It is a great thing to do. But here there are certain points that you need to observe. The network acts as if each node could be as an independent MM1 queue, even though that is really not the case. Whereas in series network they are really independent, but here they can be viewed as an independent and the joint distribution can be written as a product of modular distribution as it turns out here. The flow into each node behave as if it is, it is Poisson, okay, even though they may not really be Poisson in nature. Especially, this is especially the case when there is a feedback in the network. When there is a feedback in the network, it has been shown in the literature, or it can be shown with a little bit of effort, that the internally when the flow, if you look at into the any particular node, they need not be Poisson. Okay, one can split that further, go deeper into that. We are not going to do that. What is relevant here is in a series network, when we have only feed for R, in general feed forward network, they will be really independent. But whenever in a open Jackson network, when there is a feedback feature is there, right, the internal flows are not really Poisson. Like this has been shown long back, it is a new feature that you are talking about here. But for us to understand that a bit difficult, but it is actually the case that the internal flows is not really Poisson in general, okay, at least whenever there is a feedback. If there is no feedback, obviously it can be shown that they are truly Poisson, but otherwise it is not. But even then, the advantage at the plus point of this Jackson network, even then this result holds, even if there is a feedback. That is what is the power or the significance of this particular result that you get. Okay. So, now let us quickly verify the solution. So, what we have here is that this is the form. So, we will first show that Pn which is equal to this satisfies the balance equation, and using the normalization condition that C turns out to be this. If we have shown this, then we have shown that this is the solution to this balance equation, right. Now, recall this balance equation here. What we are going to do is we are going to plug in for this C times, in this particular case, for example, rho I to the power Ni, except that ith one alone will be Ni minus 1, right. That is what you will have. Similarly, here this is all C times rho I to the power Ni, the product of them, except that the ith one will be Ni plus 1 and the jth one will be Nj minus 1 in the power, right, because of this particular form that we are picking it up. P n bar I plus means only the ith element, it will be Ni plus 1, j I and j minus means jth element will be Nj. Once you plug it there, right, into that balance equation, then for example, this one will give me that 1 I plus was there, right. So, that is what will turn out to be here, and if I cancel it out, this quantity, right, in both sides of the equation, what we want to see that it will be whether this is equal. So, I am putting the question mark against this equality, because we want to see whether these two are equal when you put the solution in both sides of the flow balance equation, right. So, the first term here, for example, Pi P n bar I minus, so the ith one will be 1 minus. So, you multiply and divide by I, the ith quantity 1 rho I, that is what will be this, right, gamma I times divided by rho I is what then you will get here. So, the next term, all terms are in the same fashion that you will do. So, after cancelling it out, this is what you will end up with this. Okay. But now, the traffic equation is this. What we have done is that the jth one we have written down explicitly separately. Okay. So, lambda j minus gamma j minus rjj lambda j would be equal to this quantity. We want to write that. So, that is what is the case here. Now, what one can do here is that in this set, you can substitute this expression here, right. Rij lambda I for I equal to 1 to k, I not equal to j is what then you can substitute here. You will end up with j is equal to 1. Then this mu I will get cancelled, and mu j by lambda j will be here. Lambda I Rij is what this quantity for I, this whole quantity is what then would be equal to this as per this expression. Okay. Now, I can change this I because I want to combine this together. This just indices alone from I j to I can change, and I can write this together in this form, right. First term as it is, this term as it is, this term is also here, and this is here, right. Now, again you can see that this lambda I, right, lambda I and this mu I is here, summation mu I on the left side, summation mu I is on the right side, right. So, I can cancel it out, right. So, this is mu I by lambda I, gamma I here, right, gamma I mu I by lambda I, there is a plus, this is minus, this term also will go, right, Rii lambda I. So, there is one here mu I, So, lambda I will go, this is mu I r I I minus, so here also minus. So, this term also will get cancelled with this, right. You will be left with only this term on the left hand side and you will have right side only on this term. That means finally we will get this as the expression. Now, if this is true, that means the solution satisfies the balance equation. Now, you see what is this means? This is the sum of, right, flow into the network from all nodes, and this is the sum of flow out of the network from all nodes, right. So, from lambda I, ith node with probability r I 0, it goes out, right. So, this is from the ith node, it is the flow out, sum over all the nodes, and this is sum over. And for an equilibrium to hold means that this must be equal, right, and hence this is true, right. So, this is true and hence, right, the form here satisfies the balance equation. Now, we have to show C is equal to really this, which is nothing but the normalization condition, you pick normalization condition once you pick, and then you obtain C is equal to this quantity as its the what we call the quantity C is given in terms of. Now, if you plug this into this with C here, oh sorry, here there is one typo here, just have to be 1, 2 and this must be K. Fine. So, that is what you need to understand, right. So, this is what you get here, and finally, you will arrive at this as the solution. So, we have verified now the solution to this we have in fact seen the Jackson theorem essentially for single server thing. We will generalize this to the next one. Now, once we have this, then again as usual the performance measures can be obtained in a routine way. For a single channel node open Jackson network, with single channel at each node, then we can obtain Li, the number in the system or each node, and its waiting time in each node, or the system time or sojourn time in each node is this. Here really the sojourn time is what is the word used in this networks in a way for node Y. Now, this is because the product form of the joint distribution, remember, but that does not imply that the nodes are truly MM1. It is not because of that it is coming, it is because of the joint distribution factors into the product of certain marginal distribution, and from there we are getting this. That is how you are obtaining this quantity. Okay. So, the expected number of total customers in the network is summation of this, because you have to add in each node whatever number of customers, you simply add, you will get this. So, the expected total weight in the system, which is basically the sojourn time in the system for any customer before its final departure, is basically W, which is summation Li by summation gamma I. This is the total arrival rate into the network, and this is the total number of customers in the network. So, this is the total weight or the sojourn time, mean sojourn time in the network for all the customers, which is basically the Little's formula for the entire network that you have here. So, like these are straight away the performance measures that you can obtain it for ith node, and from there then you can give for the entire network. Okay. So, we will stop here and then more we will see in the next lecture. Thank you. Bye.